Imagine holding an entire, industrial scale data center right in the palm of your hand.
Yeah, which sounds like science fiction, honestly.
It really does. I mean, just a few short years ago, if you wanted to run a truly powerful multimodal AI,
Like something that could read a massive document or code.
exactly, something that could read a 300-page brief or reason through a really complex logic problem step by step, you essentially needed to rent time on a massive server farm.
Right, you were relying on huge racks of specialized chips.
And industrial cooling systems just to keep them from catching fire. But today, for this deep dive, we are looking at how Google's Gemma 4 models are basically squeezing that exact same server-level processing power into the standard smartphone sitting in your pocket.
Without instantly melting your battery, which is the really crazy part.
Right, and it's not a simple feat.
No, it is arguably one of the most difficult engineering challenges of the decade. I mean, we are no longer dealing with the infinite resources of the cloud.
We're dealing with a phone.
Exactly. A space with incredibly strict, unforgiving physical limitations. The average smartphone today might give an app, maybe 3 to 5 gigabytes of available RAM to play with?
If you're lucky.
Right, if you're lucky. And you have a mobile processor that throttles the moment it gets too hot, plus a battery that has to last all day.
So taking a massive neural network and forcing it to survive in that kind of hostile environment.
It requires tearing the entire architecture down to the studs. You have to rebuild it specifically for edge hardware.
And that is exactly what we are going to unpack today. So by the end of this deep dive, you listening right now are going to know the exact architectural magic happening natively on your phone.
The real nuts and bolts of it.
Yeah. You'll understand how these massive models are fundamentally restructured to bypass those mobile bottlenecks.
Yep.
How they process vast amounts of information without crashing your device.
And why this totally offline capability is about to shift the whole landscape of personal computing.
It's huge. So let's get right into the scale of what we are dealing with here. We are focusing on two mobile variants of Gemma 4, right? The E2B and the E4B.
Right. Let's lay out the raw specs first so we can really understand the gravity of the problem.
Okay, lay it on me.
So the smaller model, the E2B, has 35 neural layers and 5.1 billion total parameters.
Okay.
And the larger mobile variant, the E4B, bumps that up to 42 layers and 8 billion total parameters.
8 billion on a phone.
On a phone. And both of them feature an absolutely massive 128,000 token context window.
Wait, 128,000 tokens?
Yeah. That means they can hold roughly the equivalent of a 300-page book in their active short-term memory at any given second.
Wow.
And they also boast a 262,000-word vocabulary, which gives them this incredibly nuanced grasp of human language.
Okay, but let me stop you there. 8 billion parameters, or even, 5.1 billion for the smaller one. I remember when a billion parameter model was front page news and required a literal supercomputer.
Oh, absolutely.
A 5.1 billion parameter model in its standard uncompressed mathematical state is what? 10 or 20 gigabytes of pure data?
Easily. Yeah, easily. If you take standard 32-bit or even 16-bit floating point numbers.
Which is how these weights are normally stored, right?
Exactly. That's the default. The E2B model would require around 10 to 15 gigabytes of RAM just to load the file.
Just to open it.
Just to open it, let alone run any actual calculations.
So it's an immediate non-starter. Like, my phone's operating system would just kill the app instantly for demanding too much memory.
Without hesitation.
If my phone only has 3 gigabytes of free RAM, how do we get a 15 gigabyte brain to fit inside it?
Well, the foundational step here is quantization. Specifically 4-bit quantization.
Okay, 4-bit quantization.
Yeah, this is the hardware-level compression that takes that massive file and squishes it down to about 3 gigabytes.
Making it physically possible to load onto a standard device, like a Pixel or an iPhone.
Exactly. It's the only way it fits.
I'm trying to visualize how you strip away that much data without making the AI completely useless. Is it like dropping the resolution on a streaming video?
How do you mean?
Like, if I'm watching a movie in 4K, it eats up my whole data plan. But if I drop it down to 720p, I lose a little bit of crispness. Like, the leaves in the background aren't perfectly sharp, but the video loads instantly and takes up way less space.
Right.
Are we basically just lowering the AI's resolution?
That's a really common way to think about it, but it's actually a bit more severe than that.
Really?
Yeah. A better analogy would be taking a highly detailed photorealistic painting that uses, like, millions of subtle color gradients
Okay.
and forcing yourself to repaint that exact same image. using only a 16-color watercolor palette.
Wait, only 16 colors? That sounds like you'd lose the entire image. It would just be a blurry mess.
You'd actually be surprised. See, a parameter in a neural network is really just a number representing the strength of a connection between two artificial neurons. Usually it's stored with incredible precision, lots of decimal places. But 4-bit quantization forces the model to round those incredibly precise numbers into much coarser, chunkier buckets.
Oh, because 4 bits literally only gives you 16 possible values to choose from.
Exactly. You only have 16 options per weight. You lose the microgradients, absolutely.
Right.
But if the underlying structure of the painting, the shapes, the contrast, the core subject is strong enough, the 16-color version is still perfectly recognizable.
So you are definitively making the model slightly less mathematically precise.
Yes.
But the trade-off is that it finally physically fits in the room.
Precisely. If you don't quantize the model to 4-bit, it simply cannot load into mobile RAM.
And it doesn't matter how smart the AI is if the file won't even open.
Exactly. You are trading a microscopic fraction of accuracy for the fundamental ability to exist on edge hardware.
Okay, I get that. But fitting into RAM is really only the price of admission, isn't it?
It's step one.
Right. Because just because it's sitting in memory doesn't mean the processor knows what to do with it. If you take a massive cloud model and just blindly shrink it down to 4-bit, does it actually run well on a phone?
Oh, it runs terribly.
Yeah.
Awful. And that brings us to the core architectural innovation of Gemma 4. Because you can't just shrink a server model, you actually have to redesign its anatomy for the realities of a mobile processor.
Because mobile chips are built differently.
Very differently. Mobile CPUs and GPUs have a severe bottleneck when it comes to memory bandwidth. They hate having to constantly fetch data, do a really complex math equation, and then fetch more data.
Right. That back and forth is slow.
Super slow. And historically, AI models got smarter by getting deeper. They stacked dozens or hundreds of processing layers on top of each other.
And the data has to flow sequentially through every single layer to arrive at an answer.
Right. Which means the mobile processor is constantly working, constantly doing math.
And just draining the battery to zero in like 10 minutes?
Exactly. Deep stacks of sequential layers are an absolute nightmare for edge hardware. So to fix this, Gemma 4 uses a decoder-only transformer setup, which is standard, but it introduces something called per-layer embeddings, or PLE.
Okay, PLE, what does that do?
Well, it's a massive departure from traditional design. Over half of the total parameters in the E2B and E4B models are dedicated strictly to these layer-specific embedding lookups.
Wait, half the model's brain is just lookup tables?
Basically, yes.
That feels almost like cheating. Like, instead of forcing the phone to calculate a complex thought from scratch through a massive maze of layers, it's giving the AI an open book test.
That is a great way to put it, yes.
Yeah.
It can just quickly look up what it needs in a giant table.
That's wild.
It is entirely a hardware-software compromise. Let's look at why that matters to the actual silicon inside your phone.
Okay.
To an ARM chip, executing complex sequential matrix multiplication through a deep neural network requires a lot of voltage. It is exhausting for the battery. But doing a quick memory lookup operation, just finding a pre-calculated value in a massive optimized table.
It can do that in its sleep.
Silicon is incredibly fast and efficient at that.
So you're basically shifting the burden away from the part of the chip that does the heavy math and pushing it toward the part of the chip that just retrieves information.
Exactly. You are trading computationally expensive sequential processing for memory-efficient lookups.
Wow.
Per-layer embeddings boost the model's ability to understand nuance without forcing it to run through 100 deep processing layers. That's why if you look at the E2B model, it has 5.1 billion total parameters, but only 2.3 billion are what we call effective parameters during actual generation.
And let me make sure I've got that. Over half the model is basically just sitting there as a giant, highly optimized reference library waiting to be queried, rather than actively doing math all the time.
That is the mechanical reality of it, yes. It's how you get high reasoning capability without the latency and heat generation of a massive server model.
Okay, so the model fits in RAM because of 4-bit quantization, and it processes efficiently because of these per-layer embeddings.
Right.
But what happens when you actually ask it to do something massive? We mentioned that 128,000-word context window earlier.
The 300-page book.
Exactly. If I feed this thing a 300-page legal contract, or a giant repository of Python code, how does the phone not immediately catch fire?
This is where we run into the limits of standard transformer architecture.
Okay.
In a traditional model, you have global attention, which means when the AI reads a word, It looks at every single other word in its context window and mathematically compares them to understand the relationships.
Which is fine if the context is a short text message. That's easy.
Right.
But if the context is 128,000 words.
The math explodes. Attention scales quadratically.
Oh, wow.
Yeah. Comparing 128,000 words to each other over and over again requires an astronomical amount of compute memory. It would instantly overwhelm even a high-end mobile device.
It just simply cannot be done on a smartphone battery.
Exactly.
So how is Gemma 4 pulling it off? Is it just ignoring parts of the text to save time?
It's not ignoring it, but it is strictly managing how it focuses. Gemma 4 employs a hybrid attention mechanism.
Hybrid attention.
Yeah. It constantly alternates between two modes: sliding window, local attention, and periodic, full global attention.
Sliding window local attention. So instead of looking at the whole 300-page book at once, it puts on horse blinders.
Exactly.
Like it's only looking at, say, the paragraph right in front of it.
Very close. The technical spec for these mobile models is a 512 token sliding window.
Okay.
So most of the time, the model is only looking at its immediate surroundings, just the last 512 words. It processes those relationships incredibly fast, using about 16 heads at 256 dimensions. Then it slides the window forward a bit and processes the next 512.
And because the window is so small, it takes very little compute power.
Exactly.
But wait, if it's always wearing blinders, how does it know what the first page of the contract said when it reaches page 300? Doesn't it lose the thread of the conversation entirely?
It would, which is why it periodically takes the blinders off.
The periodic global attention.
Right. Every few layers, the model inserts a full global attention layer. It scans the entire 128,000-word room, recalibrates its overall understanding of the document, and then puts the blinders back on to continue processing locally.
That's incredibly smart.
And critically, the very final layer of the model is always global.
Oh, so before it answers you, it checks the big picture.
Exactly. It
Yeah.
synthesizes the entire context perfectly before generating a response. And to save memory, during those global layers, it bumps up to 512 dimensions, but uses fewer heads like 4, and shares keys and values.
That's a brilliant balancing act. You get the speed of local processing most of the time, but you keep the deep comprehension of global processing.
And the architecture actually goes even further to protect your phone's memory during this whole process with something called grouped query attention, or GQA.
Okay, I see GQA mentioned in a lot of technical breakdowns, usually alongside a terrifying alphabet soup of acronyms like PROPE, RMS norm, SWIGLU activations.
Oh yeah, the papers are dense with them.
But I rarely hear what GQA actually physically does to help the phone.
Okay, think about it this way. As the AI reads that 300-page document, it has to store its ongoing understanding of those words in a temporary scratchpad memory. We call that the KV cache.
The scratch pad, got it.
In older models, every single attention head, those are the parts of the model looking for patterns, demanded its own massive dedicated scratch pad.
Let me guess. On a mobile phone, giving everyone their own massive scratch pad eats up all your remaining RAM immediately.
Instantly. So grouped query attention forces those attention heads to share.
Oh, okay.
Imagine 4 students studying for an exam. Instead of buying 4 expensive identical textbooks, which takes up way too much space on the desk and costs too much,
Right.
GQA forces those 4 students to group together and share a single textbook.
That makes perfect sense.
The KV cache shrinks dramatically.
Eh.
It frees up vital RAM on the phone while still allowing the model to process really complex queries.
So every single feature we've talked about, from the 4-bit quantization to the lookup tables of PLE to the sliding blinders to sharing the KV cache textbooks, it all serves one master goal.
Keeping the memory footprint small and the compute cycles low.
We've basically built the perfect engine for a mobile device.
We have.
But an engine still needs a chassis, right?
Right.
How does this actually run on the phone's operating system without lagging out?
Well, the software bridge is just as vital as the model itself. The Gemma 4 models rely on highly optimized runtimes, specifically linear-T or standard transformers, to talk to the actual silicon.
Linear-T. So that's essentially the translator that takes the AI's complex math and turns it into instructions that a mobile ARM processor understands.
Exactly. Linear-T is specifically designed to leverage ARM architecture optimizations. And a massive part of that optimization involves sparse activations.
Sparse activations. Okay, we talked about how the E2B model has over 5 billion parameters. Does sparse activation mean it's not using all 5 billion of them at the same time?
Correct. If you ask the AI a question about, say, the chocolate chip cookie recipe,
It doesn't need to boot up the neural pathways that understand quantum physics.
or medieval history,
Right.
Sparse activation ensures that for any given prompt, the model only wakes up the highly specific network paths required to answer that exact query.
And the rest.
The rest of the billions of parameters remain completely dormant.
It's like it doesn't turn on every single light in the house just to read a book in the living room.
That is a perfect analogy, and honestly, this is the unsung hero of battery life.
I bet.
If you fired up all 5 billion parameters simultaneously for every single word generated, your phone would overheat in minutes. By only activating the necessary pathways, the power draw stays incredibly low.
And the performance you get out of this optimized setup is staggering. When running natively on high-end phones via apps like Google AI Edge Gallery, these models are hitting anywhere from 10 to 30 tokens per second.
Which is incredibly fast.
30 words a second. That is significantly faster than most humans can even read.
It feels instantaneous to the user. But honestly, speed isn't even the most impressive part here.
No.
No. The true breakthrough, the thing that fundamentally changes how we interact with mobile computing, is the integration of the native thinking mode.
Oh, yes. The think tag. Literally think. This is where the model goes from being a fancy autocomplete to an actual reasoning engine.
Exactly. Traditionally, when you ask a cloud AI a complex logic question, a massive server does the heavy lifting. It outlines the steps and sends the final output back to your screen.
Right.
But these Gemma 4 models feature a think capability that forces the model to engage in step-by-step reasoning completely offline.
Which is wild.
It actively breaks down a problem, outlines a logical progression, analyzes its own steps, and arrives at a reasoned conclusion, all by itself.
Without ever pinging a cell tower, I really want to emphasize how wild this is for you listening. Imagine you are a lawyer on a transatlantic flight. You are 30,000 feet in the air, airplane mode is on, you have zero Wi-Fi. You can pull up a massive, dense legal contract, feed it into your phone, and ask it to find loopholes.
Yep.
And your phone, utilizing these quantized weights, local attention windows, and sparse activations, autonomously reasons through that document step by step, generating 30 words a second.
It's incredible. Or think of a software engineer debugging thousands of lines of proprietary code in a secure facility with no internet access.
Right. The phone just ceases to be a portal to the cloud and becomes an independent, localized intelligence.
It does. But, this brings us to the ultimate reality check.
The catch.
The catch. We have to look at the fundamental trade-off of the Gemma 4 architecture, because there's no free lunch in computer science.
Right. You can't compress a 15-gigabyte brain down to 3 gigabytes, force it to use lookup tables, and make it share scratchpad memory without losing something.
Exactly. You are absolutely sacrificing a degree of absolute reasoning power and encyclopedic knowledge.
Right.
A 5 billion parameter mobile model will never beat a trillion parameter cloud leviathan in a pure intelligence test. The edge model might hallucinate slightly more often on highly obscure topics.
Or struggle with hyper-complex logical leaps that a data center model would easily clear.
Exactly. But the deliberate compromise is that in exchange for that slight dip in raw omniscient power, you are gaining massive, unprecedented advantages in privacy, speed, and localized control.
Privacy really is the dominant factor here, isn't it?
Huge. With a cloud model, every deeply personal question you ask, every proprietary company document you upload, every private health concern you query, that data leaves your device.
It travels to a corporate server, is processed, and is sent back.
Right. But with Gemma 4 running natively, the data never leaves the hardware in your hand.
It is the ultimate closed loop. The processing happens instantly, on your own silicon. You have an incredibly smart, capable assistant that works securely in the palm of your hand, even if the entire global internet goes down.
It is a profound shift in how we distribute computing power. I mean, we spent the last decade centralizing intelligence in the cloud. We are now figuring out how to successfully decentralize it, pushing it all the way out to the physical edge of the network.
It really is an engineering marvel. We've gone from the microscopic math compromises of 4-bit quantization through the clever cheat codes of per-layer embeddings, all the way up to autonomous offline reasoning in airplane mode. Thank you so much for walking us through the silicon reality of this architecture.
Oh, it was my pleasure.
But I want to leave you, our listener, with one final thought to mull over, building directly on what we just discussed about privacy and localized intelligence. We've grown incredibly accustomed to handing over our digital lives to massive cloud servers just to get a smart answer.
We really have.
But if our smartphones can now engage in complex step-by-step reasoning completely offline, with massive vocabularies and absolutely zero cloud dependency, How long until we stop trusting the cloud entirely with our most sensitive questions and start relying exclusively on the private genius sitting right there in our pockets?
That's the real question.
Think about it. We'll catch you on the next Deep Dive.